Welcome, or hopefully welcome back, to another episode of the Reliability Matters podcast. For those of you who are counting, this is episode number 157. On today's episode, we'll be exploring the critical steps to avoid contamination on circuit assemblies during the rework process with our expert guest, Gayle Towell. Gayle is the content marketing specialist at AIM Solder, a leading global manufacturer of solder assembly materials for the electronics industry. She holds a master's degree in both mathematics and physics from the University of Oregon and has nearly 2 decades of experience in higher education, technical writing, and creative writing. In her role at AIM Solder, Gayle is instrumental in producing technical and research-based materials while also collaborating with industry partners on various subjects. She has contributed articles to industry publications such as Printed Circuit Engineering Association magazine, where she discusses topics like solder paste powder sizes and mixing materials. Gayle has also participated in numerous industry events, including the Surface Mount Technology Association International Conference, where she shared her expertise in sessions covering soldering technologies and solder paste advancements. Additionally, she's appeared on podcasts discussing the development of new solder products. Her extensive background in technical communication and her role at AIM Solder highlight her significant contributions to the electronics manufacturing industry. And today, she'll be sharing her insights from a recent technical article, What's on Your Rework Bench? In this discussion, we'll review the rework station and the essential practices that can make or break circuit reliability. Gayle will walk us through the common pitfalls she's seen, from the dangers of unapproved fluxes to mismatched cleaning solvents, and explain how these mistakes lead to long-term failures in the field. She'll also share practical advice on maintaining a contamination-free bench, the importance of selecting compatible chemistries, and why regular audits and operator education are key to preventing unintended residues and contaminants. Gayle will help us prevent one problem, rework, while not creating another, contamination, when I return in just a moment. Stick around.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Hey, Gayle, welcome to the program.
Hello, happy to be here.
It's nice to see you again. We saw each other a couple of weeks ago in Chicago at the Surface Mount Technology International. I saw you up doing your thing.
Yep.
And recently you recorded a series of kind of the introduction to SMT, which was very interesting. If people are interested in hearing your take on that, they can look out for SMTA videos that'll be released soon if they haven't been already. Well, let's start kind of at the beginning. The reason for me reaching out your way was an interesting article that was published by AIM on the subject of, the title of the article was What's on Your Rework Bench? And, rework is always problematic because whenever, you rework something, there's an introduction of another level of liability and reliability. So rework obviously just needs to be done when it needs to be done. We don't rework for cosmetic reasons and things like that, but when it has to be done, it has to be done. Could you share a little bit about the inspiration for that article and what motivated AIM to focus on the rework chemistry and contamination concerns within the SMT rework space?
So as solder suppliers, so we make solder paste and we support our solder paste. And so when people use solder, they have to, there's the material itself, but there's also the process. And so a lot of times where people run into problems has nothing to do with the material we provide, but has to do with the processes they are using. And rework is one of the processes that can introduce sort of the most human variables, human error into the process. And this article, so it was originally published a while back, written by a colleague named Tim O'Neill. And I recently did the revision and updating and republishing of the article. And he had seen several instances where you go to a site and you look at the rework bench and it's either a mess or they have certain chemicals out, liquid fluxes and so on that really aren't meant for rework and can lead to a lot of problems if used in a rework situation. So the types of fluxes and materials you might use on the production line aren't always compatible with the rework process. And then people run into problems and then they don't know, they don't know if they should be blaming the materials. They don't know if they should be blaming the operators. They're trying to figure out where those problems come from. And what Tim had discovered is as many as 8 in 10 reliability issues can be traced back to the rework bench itself. And so focusing on that, we can give our customers a lot of insights into what they need to be looking out for there so they can prevent a lot of those problems.
Yeah, that's great. The article discusses the impact of using, and I'll quote the words, unapproved fluxes in rework. What are some of the most surprising types of fluxes that you've encountered at rework stations, and what were the consequences of using those unapproved fluxes?
So part of the issue with fluxes in rework, so a lot of fluxes are designed so that once they reach a certain temperature, they do their activity, they clean the metals and clean the oxidation up. And then after they've done that and reached that temperature, they're then inert. But in a rework situation, a lot of times if you're using external liquid flux, it won't reach that temperature. So if you have a board and you're sending it into an oven, everything on the board is going to get hot. So any flux you use on that board is going to activate and then it becomes inert afterwards. But on the rework bench, you're usually using a soldering iron. It's a much more focused operation. And if you use that same type of flux, not necessarily all of it's going to get heated. And so you're going to be left with flux residue that hasn't activated and become inert. And then that can lead to dendritic growth. It can lead to all sorts of electrochemical contamination issues, essentially. And so if you use the same flux that you're using on the SMT production line or the wave soldering line, and you try to use that for rework, it may not work for those reasons. There are specific fluxes designed for rework that don't need to necessarily reach those temperatures to become inactive. But another thing you can do is use cord wire in your rework. And cord wire has the flux in the core of the wire. And so you're essentially guaranteed that it's going to heat up because it's going to reach its temperature as you're melting the wire. Whereas if you had applied some external liquid flux, you would have to make sure that soldering iron touched every part of that in order to be sure that you're going to activate it and let it become inert.
Yeah, I think if I owned a contract manufacturing company or was an OEM producing assemblies, one of the first things I would do is locate all the squeeze bottles and throw them away. Cut them up, shred them, and throw them away. I think to your point, which is exceptionally valid, it's even exacerbated when one is using no clean flux and choosing not to clean it, because no clean flux, the magic behind no clean flux is that the activators, the bad actors, if left on the assembly, become activated and, in layman's terms, kind of burned off when they're exposed to certain temperatures. And that's the first stage. The second stage is an encapsulation process where a lot of the activators are encapsulated in a rosin layer and left otherwise inert. And if someone takes that dreaded squeeze bottle and generously applies flux like they have a relative in the flux business, then that can lead to the potential to leave activated residues, which are problematic in many ways, on the assembly, and not allow the encapsulation process to take place. And because the bottle says no clean, many
Yeah, then
people
they'd be
take
stuck
that
in
as an
there, and it'll be fun.
right, and a lot of assemblers take that as an instruction rather than just a flux type. So, when it says no clean, they may read don't clean or interpret it as don't clean. And that can be quite problematic. Another problem I've seen, to your same point, is a lot of times they'll use the same flux. Say they have a wave solder machine, for example, and they'll use the same flux that they use in the wave solder machine, which is generally a foaming flux. And the foaming agents are designed to become inert at certain temperatures. And if they are planning on cleaning the board and they over-apply flux, and it's a foaming flux, and then they don't activate the foaming agents and turn them into an inert status, then they put the boards in the cleaner, and all of a sudden it looks like a episode of I Love Lucy. Foam just starts coming out of all the crevices of the machine, and they can't figure out why. And that is frequently a cause, excessive unactivated flux with the foaming agents intact, ready to party upon agitation, which a cleaning process clearly provides. So, yeah, I think the core solder is undervalued. But there are cases where there are legitimate cases due to thermal issues and ground planes and things like that, or very large, high mass components where extra flux has to be added. And I think, to your point, it's exceptionally important to only apply flux to areas where the soldering iron is going to come into direct contact. That's a big problem within the cleaning world. In
And
more
there
ways than
are
one.
liquid fluxes that are designed to be used in rework. And that's sort of the key is sometimes people think, if I'm reworking with the same alloy, the same board, I can use the same flux that we used on the wave or the SMT line. But those fluxes are designed for that process. So they're
Right.
not just to go with the alloy and the board. They're for the process. And so
Right.
when you're reworking, it's a different process and you need to use a different material for that.
Right. They're designed to be aerosoled or in a spray fluxer, or they're designed to foam in a foam fluxer. They're not designed to just be coming out of the needle of a squeeze bottle, which should be thrown in the garbage. How common is human error in introducing incorrect fluxes during rework, and what systems or training have you found effective in preventing this human error?
So, anytime you have humans, you have human error. And so rework is all human. So the opportunity for error is much greater. And it can vary widely from place to place because different companies will have different processes in place. When things are moving fast and you just know you need flux and you just grab something that says flux, there you have a problem. So doing something like having a clear inventory system, color coding labels, like making sure that anything that can be used on the rework bench will have a certain colored label on it, or the flux that's for that is clearly labeled for that, and flux that is for other purposes says do not use on rework, right? So making sure everything's very clearly labeled with what to do and what not to do with it. But also training everybody. So anyone who's going to be using the materials should understand which ones to use, which ones not to use, and why. For me personally, I need to know why. If no one tells me why, it doesn't stick in my head. And I think that's true for most people. If you tell them why you can't use this flux, but why the other flux is okay, then that sticks with them. And then you have a nice clear labeling system. You can grab your product as you're moving quickly, and you know it's the right one.
Yeah, that makes a lot of sense. You mentioned in the article, or the article mentioned a warehouse mix-up that led to a significant issue. How do large-scale production facilities generally prevent such errors, and what are some of the challenges in that?
Yeah, so the larger scale your facility, the more you need really good processes in place and really good labeling and inventory systems. Some large scale facilities will use sophisticated systems with barcodes and real-time tracking, and that sort of prevents mistakes. Anytime you can incorporate some technology that's going to give you an alert and tell you, no, don't use this, or you have to run something through the barcode before you take it to the rework bench or whatever it is you're using it for, and it alerts you whether or not that's okay or not, then that's going to help catch those problems. But the other thing to do is just regular audits of your process, looking at everything from start to finish and identifying places where either something is already incorrect or where it might be really easy for a human to accidentally grab the wrong thing, and just moving products, labeling products in such a way that that's less likely to happen.
Yeah. Can you explain the risks associated with partial cleaning, whether it's no clean or any kind of flux? I've often said, when I give lectures and papers, that cleaning is a go big or go home process. There's no such thing as being partially clean. Give me some facts behind a statement like that. Why is partially cleaning or cleaning in an ineffective manner worse on an assembly than just not cleaning at all?
Yeah. There's a few different types of flux residues that might be left behind, right? So you might have no clean flux residue, you might have water-soluble flux residue, or you might have a residue that requires a special cleaning solution. So if we think of water-soluble flux residue, it gets rinsed off very well with water, but if you leave any of it on there, then, and especially if there's a little bit of water left with it, that sort of gives you all the ingredients you need for stuff to start growing, for like electrochemical migration. The electronic components will grow these little dendrites could eventually, if the residue is bridging two conductive parts, it can then bridge those two conductive parts and create a short. The same is true if you have like something you have to use a special cleaning solution for. If you don't quite get it all clean, you don't quite get it all off, what you have left on your board is some sort of new chemical mixture with your flux residue, with your cleaning materials, and that can again create an environment where you can end up with shorts, you can end up with corrosion, and so on. No clean flux is designed to stay on the board without causing issues. So you can, once that flux has been activated, it becomes inert, and it's passed to be called a no clean flux. It's passed all sorts of tests so that the residue is not going to enable that dendritic growth. It's not going to cause corrosion or cause any problems with the board or lead to shorts. But if you partially clean it, or if you haven't activated the residue because you were using an improper flux in a hand soldering operation, then again, you get material on your board that is some combination of flux residue, cleaning solvent, some water, and that's just a recipe for corrosion and all sorts of, you could lead to shorts and damage and so on. So you either need to get all of it off, or if it's no clean, you make sure it's activated and you just leave it alone. The partial cleaning basically just introduces more chemicals and more interesting stuff into the mix that can just create more problems down the line.
Yeah, that's a really good point. The worst thing that someone can leave on a board is wash solution. The chemicals that are used to solubilize the flux residues and put them into solution are highly ionic and highly corrosive. They generally, not all, but most of the chemicals used in defluxing applications are high on the pH scale. And if you want to see all your solder joints turn black within, an hour or two, don't rinse the board or don't rinse it properly. That's a good point. Another point, kind of going back to what we talked about a couple of questions ago about putting too much flux on a board and not having it properly activated and turned inert, is if someone's running a no clean flux through a reflow oven, for example, it's very important that the profile on the oven be what they think it is, what they intended it to be. We produced a DOE and presented a paper with some industry colleagues, Foresight, which is an analytical laboratory that specializes in contamination. And we ran an array of assemblies at various peak reflow temperatures, starting at the minimum recommended peak reflow temperature from the solder paste manufacturer. And then we took it down 1 or 2%, ran more boards, and then brought it down another couple of percent, ran boards. And when we hit the 4 to 5% below peak reflow temperature mark, all the boards failed surface insulation resistance or SIR testing, all of them. And it's not a far stretch of the imagination to think that a reflow oven, the profile could drift. There's a lot of factors, not just what they set, but the state of the vents and how much residue is clogged up in it and whatever the case may be. And if someone ran a golden board and they determined that everything was perfect the day they ran their test board, and then they subjected the test board to SIR and they got flying colors, it's important that the exact same parameters are used on every production board following that, because if it drifts a tiny bit, may not be enough to cause cold solder joints or any visual indication of a defect.
And that's the worst, the defect that you can't see.
That you can't see until 6 or 8 months later or a year later, and all of a sudden you have all these RMAs coming back. And we determined that around the 4% below minimum peak temperature was the point where we went from a high pass from an SIR standpoint to a very substantial fail in SIR. So that's an important factor as well. No Clean is a magical product in how it works, but it has to be given it has to be given a chance to work. The article mentions, I mentioned before, first thing I would do if I owned one of these companies is throw out all the squeeze bottles. I think the second thing I would throw out are all the little IPA pumper bottles that I see on tech benches. And the article mentions the ineffectiveness of isopropyl alcohol, or IPA, as a cleaning agent for certain flux residues. What other solvents? Well, first of all, why is IPA ineffective for many species of flux residues? And what other types of manual cleaning solvents would you recommend, and under what circumstances?
Yeah, so IPA, a lot of people sort of use that as this will work for cleaning anything, but it doesn't, right? So it's not always a perfect solvent. It doesn't always work on every type of chemical. And so assuming that it does leads to problems. And then once you start putting that IPA on some chemicals and you don't know what it's doing, you don't know what that interaction is, and you don't necessarily get it all off, now you have entirely new chemicals on your board. IPA combined with whatever remained in the flux residue. And without testing, without knowing what that combination creates, it's hard to know what's going to happen to that board. Maybe it'll be fine, or maybe you're going to get corrosion. Maybe you're going to get shorts. Maybe it won't have you thought it was going to clean off your no clean. The thing about no clean flux is you're meant to not clean it, but if you do want to clean it, you better clean it good, and it doesn't dissolve easily. So it requires special chemicals in order to get it all off. You try to clean that off with IPA, it's not going to work. You're in that partial cleaning situation again. So when it comes to what chemicals to use to clean, there's no sort of one answer for that. Again, it depends on the flux chemistry. So water-soluble flux is great. You can clean it with water. But anything else, usually you need to talk to the solder supplier or work with one of the cleaning companies, and they might have a matrix of which cleaning chemistries work best for each situation and for each product. So the exact chemistry varies depending upon the application.
I started my business in the cleaning equipment industry in 1992. Guess what else came out around that time? No Clean Flux. It's like, could there have been any worse timing? And back then when No Clean first came out, I think Multicore's X32 was the first, or one of the first No Cleans that I saw anyway. And it had two negative attributes alongside the very positive claim that it would not have to be cleaned. The negative attributes were it was difficult to solder with back in those days because it was very weak. It was a super low solids flux, and those solids were there for a reason, right? So your solder joints had to be very clean. They had to be fresh. A lot of wave solder machines were suddenly inerted in nitrogen to help the soldering process, because back then No Clean needed that extra assistance. The other kind of negative attribute to the early days of no clean fluxes were the fact that they were notoriously difficult to clean. We weren't used to that. We were used to RMA, which was very easy to clean compared to no clean. And then no clean came out, and all of a sudden the myriad of chemicals that our industry was using were marginally effective. We had more heat required. We had longer cycle times required, and they were not easy to clean because cleaning of the no clean was not in the radar of the manufacturers at the time because it's no clean. No one's going to want to clean it. Today, I've seen pretty much a 180-degree turnaround. They are much easier to clean, and I'm not sure. Well, I have a feeling it has to do with a combination of the chemical ingredients in the no cleans today are just organically a little easier to clean. Still a little bit more challenging than other flux types, but a lot easier than they used to be. And the chemicals have come a long way as well. So I think that combination has helped. The issue, I think, though, that a lot of people overlook is the flux may indeed, if everything is performed properly, be inert and not pose a problem on its own. But when the decision is made to not clean, or when the decision is made to not remove the flux, it is a parallel decision to not remove anything. And the tolerance for residues has drifted down over the years due to miniaturization, basically. The closer components are together, the closer conductors are together, cathodes and anodes, the less tolerance for residue. So we routinely, annually, do a poll with our customers and people that are cleaning assemblies as to what type of flux are you removing. And overwhelmingly, the answer is no clean. More people are cleaning no clean than any other single species of flux.
The flux design cannot be cleaned.
Exactly. Yeah, there's a world of ironies here, right? Part of it is the fact that no clean is the most popular flux in production
so if you're
today.
already using it for everything else, you're using it for
exactly. So so we tell people, like, don't change your flux just because you're going to clean. Just run everything with no clean if that's what you're doing, and then clean what has to be cleaned, right? So part of that poll is a little bit deceptive. Not everyone is cleaning it because there's something wrong. They're cleaning it because it requires cleaning either by spec or customer requirement, and that's the flux they're using. But it is a interesting irony that that's the case.
Yeah, I mean, one thing we're seeing a little bit of is once people start getting into the ultra fine pastes and they're working with the really tiny components that are all close together. Some places that had always been using no clean are just switching back to water soluble because they're going to need to clean it anyway, and water soluble is easier to clean.
Yeah. If you'll allow me to stray off topic just for a moment and drill down that rabbit hole a little bit more, I think it is best practice to run some degree of chemical, even if one is cleaning or removing water-soluble flux. Water-soluble flux is inherently easier to clean because it is already soluble in water, assuming the reflow profile didn't burn it on.
Other things on the board too that you're trying to clean off. At the same time.
Some of the usual suspect residues dragged over from component and board fabrication and other assembly processes and dirty humans may contain residues which are hydrophobic, and water doesn't have any power over them. So to me, if someone's going to clean everything, right? Because the tolerance for residues is so low today, as I mentioned earlier, that it's the totality of the residues that may be problematic, which is for assemblers who are cleaning no clean, as ironic as that sounds and counterintuitive as that sounds, they're doing it not because the no clean flux is inherently contaminating, but the totality of all the usual suspect residues may cause them to do it. Not everyone needs to do that, but For those that
Yeah.
have to, they have to. And if you're going to have to, yeah, you can run water-soluble flux. There's other advantages to OA flux, and that is it's more aggressive. It's a little easier to reflow, particularly if your components are aged and maybe a little bit tarnished or corroded. It's a powerful flux. But if you do run water-soluble, yeah, you kind of need to clean it in a timely fashion because it remains active and corrosive until it's cleaned. You touched on potential issues arising from multiple fluxes with incompatible chemistries. I'd like to know what is an example of incompatible chemistries, and what are the steps companies take to test compatibility to avoid those issues?
Yeah. So again, different fluxes are designed for different applications. And a lot of times, if you're getting all of your fluxes from the same provider, they may have already done a lot of testing to make sure the chemistries of all of their fluxes are compatible with each other, but that's not always the case. And so once you have two different chemicals that have different properties, and then you mix them together, you can get an entirely new thing, right? You can get some reactions between what's in the two chemicals, and now you have something and you don't know what it is. So it's a matter of you're dealing with a chemistry and you don't know what it is. So you may need to run some tests to see if it works well. You may need to use both fluxes and then do some SIR or iron chromatography testing just to see what you have now, right? Because if you're getting any chemical reactions between the two different chemistries, you may be getting entirely new chemicals in there that weren't in the individual fluxes themselves. So it's always important to know that once you start mixing two different things together, what you end up with is some new thing you have to understand, right? So if you're working with a single supplier for different flux chemistries, they may already have done this testing to see the compatibilities, but that's not always the case. And you may need to run some of that testing yourself if you're going to try to use different chemistries alongside each other, just to make sure that everything still meets the criteria it needs to meet.
I understand going to the material supplier and saying, hey, I'm running XYZ solder paste. What chemical would you recommend? Obviously, companies like yours and others probably have a database of compatibility. But how would someone run that test themselves in-house? What types of tests should they run? Should they just try it and see if it fails? Or are there kind of go-to methods for determining compatibility, short of asking the supplier?
I think it really depends on the application. But in general, how I would imagine going about it is determine what it is you're trying to use, perform the process on a couple of boards, and then do all of the standard testing like we usually do when we've developed a new paste. If you're not going to clean it, you do the SIR testing. You might do ion chromatography to see what chemicals are in there and if any of them pose a risk, and so on. So just basically run a few boards using the combination and then do all of the testing you would do on a new material to make sure it meets your specifications.
Great. The article, What's on Your Rework Bench, for those who joined us late, mentions a special reserve flux and for contaminants for components with poor compatibility. Special reserve sounds like a wine more than a flux. Tell me what a special reserve flux is and how can companies determine the right balance between flux activity and reliability in these cases?
That's always a tricky situation, right? So higher activity fluxes make it easier to solder difficult components, but they leave behind residues that are, potentially more problematic, and you need to make sure they're fully cleaned. So again, this is something you'll want to usually try it out on some test boards and perform some tests to make sure everything still stays within specifications once you perform whatever cleaning process you want to do. So just making sure that you have enough activity in the flux that it's cleaning the components, but no more than you absolutely need, and that you have a qualified process for cleaning off any residue and verifying that that residue is indeed gone and you haven't created a monster by the end.
Yeah. For operators handling rework, what are some of the key educational practices or audits that you find crucial in maintaining quality?
So definitely we like to promote the use of cored solder wire because the flux is in the core of the wire. It's going to get heated as you are applying the soldering iron to it, and you're not going to have as much of that issue with unactivated flux that could be contaminating your board. Like you said, throw away all the squirt bottles, right? But the other thing is just to make sure all the operators are trained. There's all sorts of training. I mean, IPC has a whole series of classes on how to properly solder things, what to look for, what to avoid. Making sure that they don't just know what to do, but they know why they're doing it. Well, the more that people know why they're doing it, they know what to do when unusual situations arise. They can usually figure out what makes sense to do. And then just make sure, everyone knows which materials are okay to use, which are not. And then what are our cleaning protocols? Like if there's residue, how is this board being cleaned? And then just checking every so often to make sure the processes are being followed consistently. Making sure people have a really clear reference or a checklist of things to look at, especially if they're dealing with, rework could be a very varied job. You might be reworking different components at different times, and there may be different checklists depending on the situation.
Can you elaborate on the role of feedback loops between failure analysis and rework operations, and how does this communication improve the overall process?
I think feedback loops are basically just periodically revisiting and going over something and revising a process. It applies to just about anything in production, in life. So if a failure analysis finds there's electrochemical contamination at a rework step, you go straight back to the team, you adjust the process, you retrain them as needed, and hopefully that takes. And then next time around, so you keep revisiting it. You revisit it again, make sure there's still no problems. If you find something, you tweak the process, you revisit it again. So anytime there's something that's that critical where it's very easy for there to be error introduced into the situation, the more you can sort of constantly be reviewing the steps and making little tweaks each time you go through it to sort of modify and improve it, the better. That's sort of, I know in software development, that's kind of like their standard way they do it, is little bitty cycles over and over again to revise things. And I think that process works with just about anything.
Yeah, back in my early days of my career, I coded all the software for our machines. I'm not a software coder by any kind of training. I'm a bit of a hack, but back in the earliest days, I couldn't afford to hire a software guy or a gal, so I did it myself, and I learned the hard way: make a change, run the code. Make a change, compile it, run the code.
Yeah,
because if I
make too many changes at once, and then you get a disaster.
Get a disaster, then you have to go figure out which part of that code created the disaster. So same process. I follow the same process with video editing and all the other things I do that are complex. It's like, one step at a time.
Incremental changes frequently versus...
Absolutely. It takes a little longer. It seems to take a little longer in the production part, but it is a net savings overall. I believe the article referenced, if I remember right, an audit checklist. Does that make sense? Which I think I read it in the article. Maybe I read it somewhere else, but it was quite insightful. Are there specific areas or items that are often overlooked during audits?
That can definitely vary from situation to situation. I mean, all of this varies from situation to situation.
Sure, of course.
But, making sure there's like a regular plan for checking expiration dates of fluxes, periodically verifying how the operators are doing their work, making sure any equipment that requires calibration is that calibration is checked. I know you had talked a little bit about the reflow oven and not knowing if the temperatures had drifted. And so you put in your golden board and you put the thermocouples on there and you directly measure it to make sure, right? So that kind of thing can go a long way. So just making sure you're always, you're checking expiration, you're checking anything that requires calibration is calibrated regularly and checked regularly in case it drifts. And just maybe periodically even testing the residues left on a board to make sure you aren't leaving anything behind that nobody can see and nobody thinks is a problem until the product is out in the field. So creating a checklist can help. And if things do fall through the cracks, to add them through the checklist for next time. That's that whole loop again of always improving what you're doing.
Yeah, the checklist just organically gets longer and longer the more something's in production.
Full-time job is checklists all day.
Yeah. I wasn't planning on asking you this, but on the subject of solder pastes, I believe it's been my experience that people will, they'll keep the solder paste in the fridge, which they're supposed to do. Then they'll open it up and mix it, use some of it, and then throw it back in the fridge. Forever, because they think, well, it's like mayonnaise. As long as you put it back in the fridge, it's good till the original expiration date. But I don't think that's the way it really works in the solder paste world, right? Once you open it, that pretty much the expiration date on the jar no longer applies. Is that a correct statement?
That's true. So once you have taken it out of refrigeration, you let it reach room temperature, you stir it, you use it. You don't put it back in the fridge because at that point, you run the risk of condensation forming in the paste. So, you put your cold can of soda out and that condensation forms, right? Once you take the solder back out of the fridge again, you can get condensation directly on the paste.
On the inside of the jar.
Yeah. And then that obviously is a big, big problem. Now your paste isn't, you get that water in there, you're going to get corrosion, you're going to have, all sorts of problems with your paste when you try to use it. So the paste doesn't need to necessarily be used like the day it's opened. Usually for most paste, they'll last for several weeks at room temperature. So the general process is, when you're ready to use it, you take it out of the fridge, you leave it alone and let it reach room temperature naturally. Because again, if you try to open it too soon, you run the risk of condensation forming on the paste. Once it's reached room temperature, you open it, you stir it gently, and then you use it all up without putting it back in the fridge. But you can use it over the course of several weeks and it should still work fine.
Several weeks. Okay. So it's not a question. I think a lot of people put it back in the fridge because they only used a spoonful of flux of paste, and they don't want to throw away the whole jar and buy another jar. So they try and milk it and get it going longer. I think the fly in the ointment is that if you were to take it out of the fridge, scoop some out, reseal it, put it back in the fridge, and then let what you took out get to room temperature, would that not alleviate the condensation concern, or are there other factors that once you open it?
Scooped it out of the container, right? It's like when you take a soda out of the fridge and you set it on the counter, condensation forms on it.
Yeah.
So that's why until it's reached its final temperature.
For my audience who are trying to squeeze every bit of life out of a jar, what if we took it out of the fridge, quickly removed a various amount of content, put it on a sterile plate, and then shoved it back in the fridge before the jar had a chance to acquire room temperature? It would not be seen a big thermal difference. If I took a Coke out of the fridge, poured some of it in a glass, and then stuck it back in there. Well, it's still cold. But then what's happening on glass too? The glass is now getting that condensation, right? So the little bit you took out. Ah, there you go.
Started exposing.
You're throwing a bunch of flies in my ointment here.
How bad it's going to get can vary. It can vary based on what the humidity is. It can vary based on how big of a temperature difference there was. So can you still use it? I mean, you can always still use it. Will it work well is the question, right? It might be disastrous. And then you've basically just, not only did you not get to use that extra paste, but you've ruined a whole bunch of boards. So the net cost is not in your favor for trying.
What I heard you say is quit being cheap, Mike. Just do it right. Yeah.
Yes.
We talked about under-activating fluxes and how that can cause some long-term corrosion issues and contamination issues. How can process engineers detect and prevent the under-activating of fluxes? When you're using a soldering iron, good soldering irons might show the temperature of the tip on the base station, but that's not necessarily the temperature of the area where the tip is contacting.
Exactly.
Are there best practice methods? Yeah.
Don't use flux that requires activation to become inert when hand soldering, essentially, is the moral of the story there. You could always, if you ended up using flux like that, you can always sort of bake the boards to try to activate it and burn it off afterwards. Of course, you run the risk of damaging components or reflowing already melted or already solidified solder and stuff like that. So that's why in general we say don't use spray flux, don't use flux that requires that hitting that activation temperature as external flux when you're doing rework. If you're running a board through an SMT line and you have all the solder paste on there, in general, if you have a good reflow profile, everything's going to reach that temperature and it'll be fine. But you could still have issues if you have a lot of some components on the board have a very heavy large thermal mass, right? Yeah. And so they're not quite getting up to temperature before the board's made it through the oven. And so there's all sorts of things to consider there as well. But that sort of thing could be checked with, your golden board, sending it through, making sure you're putting your thermocouples on the heavy thermal mass items to make sure they're getting to that temperature before they move through the oven.
Yeah, that makes sense. I guess one can be not to the point where it impacts solderability and proper wetting and all that, but I guess someone can be a little bit careless when it comes to properly activating the temperature of the flux if they were planning on cleaning, not being concerned about the potential foaming issue, right? Cleaning very well, right? Because if it is going to be cleaned and you do get a little extra flux inadvertently or advertently on there, outside of the potential for foaming, as long as it's going to be cleaned, no harm, no foul. Again, as long as it doesn't impact, you don't want a 100-degree soldering iron. You're just going to, you don't want to do solder sculpting. You don't want cold solder joints.
If you've got your cleaning process tuned to the typical amounts of flux on a board, and then you put a rework board in there that has a whole bunch of extra flux on it,
right?
The same process might not get all of that off.
Right. So it's best to control the process and monitor the process and audit the process in real time to prevent rework after rework, right? We don't want that. What advice would you give to companies looking to enhance electrochemical reliability in their rework processes? And are there new technologies or methods that offer improved reliability?
So like you said, throw away all the squirt bottles, use the cord flux, cord wire. And again, just the regular process audits and all of that. So make sure if you are using an external flux, you're using one that was designed for rework. And then just, like we've mentioned earlier, monitoring the processes, making sure you're using the right cleaning solvents. You've talked to your suppliers and you know that whatever solvent you're using on your reflow boards, that's also going to work on the flux that you're using on the reworked boards, or if you need something different and so on. So as far as, the biggest... When will technology overcome human error? I think that's going to be when we get all of the AI robots handling everything for us, but we're not there yet, obviously. So people make errors. So don't let people get too tired. Make sure they have visual cues like labeled bottles. Make sure that they are regularly trained. Make sure that they're not foregoing any of their breaks. And so they're making more errors because of that.
Fatigue.
Yeah, a big part of everything is process. So the products only go so far. The process and the people involved are a huge piece of how well things will work in the end.
And have you heard anecdotes from the field of, you started the conversation earlier with, messy rework benches. And there are two types of contaminants that can land on an assembly. There are those created by the reflow process itself and prior processes, board fab and component fab and humans process residues, and then of course flux. But there's also foreign object debris, or FOD, which is equally problematic, particularly if someone's going to conformal coat the boards and other things. How important, and I've kind of answered the question in the question, but from your vantage point, how important is the cleanliness of the rework station? And have you heard of anecdotes in the field where even if they rework it properly, they activate the flux, et cetera, et cetera, et cetera, what other forms of contamination, based on your experience, can be picked up by not maintaining a fairly sterile work environment on a rework bench?
I mean, anything that's there that shouldn't be. A lot of times best practice is to make sure anywhere you have your production line or your rework benches, that is a clearly labeled zone in your facility, so that like nobody enters that zone unless they are wearing the proper equipment, they have gloves on their hands so they're not transferring hand oils, they're not eating food there, they're not doing any of that, right? So you make sure the zone that they go into is clearly labeled and separated from everywhere else, and you make sure to pass into that zone. You have to be properly attired and so on. You don't want bits of fabric. You don't want even just like metal debris from components that have been damaged or anything getting there. And then I think on top of that, just making sure you're regularly cleaning your rework space to make sure anything that does accumulate over time is removed. So there's all sorts of ways. I mean, we can all imagine the myriad of ways things can get contaminated because there's just materials floating around in the air. There's oils on your hands. There's stuff on the fabric you wear. And any of that can contaminate a board. And so just making sure you've created a zone where that can't enter and where you eliminate that as much as possible can go a long way in preventing that.
Yeah, on the subject of gloves, one of my pet peeves, I've toured, in my line of work, I've toured a lot of factory floors and assembly lines, and I can't tell you how many times people will take their gloves off and stick them in their lint-filled ESD smock pockets and then use them again. And I'm thinking, these are disposable gloves. They're pretty cheap. Throw them out. And
yeah.
I'm being facetious when I say this, but if I was forced to pick up a board that I knew had some value to it with my bare hands, I would hold it far differently than I would if I was wearing gloves. I would hold it by the edges of the board so that my fingers touched each opposite diagonal edge and have very little surface area of my fingers touching the board. I would be very aware that I don't want to put my hand oils on the board. When I'm wearing gloves, I'll totally manhandle a board, right? And if those gloves are not clean,
yeah.
I mean, we may not be transferring finger oils to the board, but everything I've watched people, in one case, I saw people eating lunch with their gloves. I'm like, great. I don't know what mayo does to a board. What type of contamination does that lead to?
I know. One of the talks at SMTAI, I think they were talking about seeing what kind of contaminants do to a board, and they were passing boards around the lunchroom to just see what got left over on there. And it wasn't a pretty picture.
Yeah, I like to call that. My friend Eric Camden from Foresight likes to call that the Dorito effect or the Cheeto effect. And anecdotally, one of the products we manufacture are ionic contamination testers, ROSE testers, resistivity of solvent extract testers, and we had a customer contact us once that said, they're seeing a spike in contamination throughout the day, but it's the same time every day. And I'm like, well, what time is it?
Like 1 o'clock.
1 o'clock. It was 1 o'clock. And it's like, okay, yeah, well, you need to talk to your operators about washing their hands and putting their gloves back on, or taking their gloves off to eat and then putting their gloves back on.
Getting new gloves after lunch.
Getting new gloves every time. Yeah. It was very basic, but it was I found it comical. I mean, it's sad considering that these boards are going into things that are expected to work more than a few days, but it was a reminder that everything that's on us gets transferred, right? So we need to have nothing on us that will be contacting the assembly, and that includes changing your gloves out from time to time. Before we wrap up, Gayle, when I was researching your bio, I noticed that you had a couple of degrees. One was physics, and was the other mathematics? Am I right on that, or is it? Yeah. So tell me how a physics person and a mathematics person is in the soldering materials business, and what unique insight in technical writing does that background bring?
Well, so my background's a little strange. So I had master's degrees in math and physics, and then I spent, when my kids were younger, I taught at community college for years and years.
Right.
And during that time, I also did a lot of creative writing and stuff like that. And then I was trying to pivot out of teaching, and very quickly discovered that people who can both write well and explain things and understand complex technical subject matter, they're hard to find, and people like them. So
very, very hard to find.
Yeah. And I was freelancing for a while, and then I landed my job at AIM when they were looking for someone with a weird set of skills, and they weren't sure they were going to find the right fit. And I'm in a role right now where I get to play with everything from these sort of, high level research projects of, what we just did. We just did an AOI study to see the sheen of different solder alloys and how those affect things. And I've done some work with low temperature solder use cases. So the super highly technical, writing the research paper, giving the presentation, and understanding all of that, to the creating the more public facing summary of that anyone can understand, to creating quick and easy answers to common problems, to doing more marketing type activities of just explaining the value and worth of our products. And so I like to tell people I do everything from the hard science to the social science and everything in between. And it's fun for me. I like that combination. I like that spectrum. And it gives me a lot of opportunity to make use of my teaching background, because I get to do interviews and videos and presentations. And I was working with SMTA on that Intro to SMT video, because they're trying to revamp their curriculum to be more engaging. And I was like, well, I can do that. I can speak to people. I can explain things. And it's nice. It's like I found a really good fit for my unusual set of skills. And that's how I got here.
Well, you certainly do a good job at that. That reminds me, I'm the conference chair for the SMTA Pan-Pacific Strategic Electronics Symposium, which we like to call PANPAC. And we always bring in, it's a very high-level conference. It's kind of the conference of interesting things. And it's you're not going to go to that conference to learn how to solve voiding. That's every other conference. It's a bit higher level than that. And I was very interested in, quantum mechanics and quantum computing. And I invited a speaker who ended up keynoting our conference, who is a PhD professor at an Ivy League university. And I'm like, great, I'll finally, part of it was self-serving, because I'd really, I understand the term quantum.
Mechanics. And then you're apparently nobody understands.
Right. Well, I had him come out, and he spoke for an hour, and I feel like it was the opposite of learning. I feel like after an hour of hearing him describe what an introduction to quantum mechanics was, I knew less than I did going in.
Yeah, it's very counterintuitive.
Totally counterintuitive. And I ended up having him on this show a few years ago, trying, another bite at the apple, explain to me in kindergarten terms what quantum is, what makes quantum versus just regular computing or mathematics or, machine, all that. And he did a better job. And I'm not sure if he appreciated it. I told him, I said, you're like an anti-teacher. I said, you sucked knowledge from my head, or what I perceived was knowledge. And that was probably the first step.
Very common take on like people who attempt to understand quantum mechanics is like, because it's paradoxical in a lot of ways. And one of those ways is it is actually deterministic, except that it's based on probabilities, which people have a hard time sort of reconciling that. And then how can then something be two different types of things at once, but picks one only when you measure it? And how does that work? And
right.
A big part of it is just accepting that that's what it is. That's just what it is. And
humans want to know that 1 plus 1 is...
That's what we have.
Yeah, humans want to know 1 plus 1 is 2. Definitive. As opposed to, well, the probability in this scenario is that it's 2. In another scenario, it might be, 4. And that's hard to put one's mind around. But clearly you've mastered both disciplines of understanding complex theories and structures and concepts and being able to explain it.
To understand everything. And when it comes to understanding everything, that sort of drove me into physics. Like, well, what's the science that really gets at the root of reality? And that's how I ended up there.
Yeah, when I speak, I think frequently is probably too great a word, but fairly routinely, I get a comment from a fellow speaker like, your stuff's a little too basic, and people want to go deep. And I kind of share your model of, it doesn't matter what I say. It doesn't matter what I know. What matters is what is received and what is understood, what's digested. So I speak about cleaning and cleanliness quantification and all that stuff. And almost every time I'm done speaking, after the public Q&A, as I'm packing up my stuff, someone will come up to me and they'll kind of look around, look to the left, look to the right, just to make sure no one else can hear them. And they'll kind of, in a low tone, say, "Thank you. I finally understand. Thank you."
So much of that, so in electronics manufacturing, the one thing I noticed first, because I'm responsible basically for generating a lot of content and explanations, there are so many topics that you Google them and all you can find are research papers. Nobody has just written let me tell you what you need to know, why it works this way, and what to do with this information stuff. And so I'm really working on trying to just create more content of that nature of like, have you ever wondered about this? I mean, one thing comes up all the time is dross generation and wave soldering. How much dross is normal? And that's like a super involved question. Nobody answers.
Right. Well, they don't want to be pinned to it. Like you said, X number of ounces.
Well, it depends on all of these things. So you can really only compare in specific. Yeah. But nobody actually says that. They just either give nebulous answers or there's no answers.
That reminds me of the old Hollis days. Hollis made wave soldering machines way back in the day, and they had I think it was unique to them, it may have been patented, an oil intermix system. So they basically covered the surface of the solder pot with oil, and the purpose was to reduce dross. But it was a mess. I mean, you did experience less dross, but you can imagine what that machine was like. It was oil on top of molten solder. It was crazy. Yeah, it was. When things went bad, it went really bad because oil would go everywhere. But
just use nitrogen instead.
Use good old nitrogen. That helps. Yeah, absolutely. Well, Gayle, thank you so much for spending all this time with me and my audience. For my audience who would like to get in touch with Gayle, I'll put Gayle's contact information in the show notes. I'll also put a link to the article, What's on Your Rework Bench, in the show notes. So if you're watching this on YouTube, right down here, just expand the information box and you'll see information on Gayle's contact information and the article. And if you're listening to this on your favorite podcast episode, when you're done driving, click on your favorite podcast site and look at the show notes, and that information will be there as well. Gayle Towell, thank you so much for being my guest today, and thanks for making complex subjects easy to understand. That's a gift more than a skill, and I appreciate that gift that you have. So does our industry.
Anytime.
Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on your favorite podcast app. If you're watching this podcast on the Reliability Matters YouTube channel, be sure to like and subscribe to the podcast to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of every month. A special thanks to Printed Circuit Engineering Association's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks also for your questions and episode suggestions. Please keep them coming. I love to hear from you. Send comments or episode suggestions to Mike at mikeconrad.com. Just remember that's Conrad spelled with a K. To learn more about the podcast, visit the Reliability Matters Podcast website at reliabilitymatterspodcast.com. Once again, thanks for listening or watching. Until next time, stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.